Section 7.2, areas in the plane. So this section is similarly related to when we did Riemann sums and finding the area of various rectangles and adding them all together to find the integral. So the steps are: model the region we want to measure in terms of continuous functions on a closed interval a to b. So for this example, we have two functions. We have an upper curve, which represents one function, and a lower curve, which represents another. We are trying to find the area between these two functions. So we're trying to figure out what this area of the shaded region is. And to do that, we're going to split that shaded region into smaller rectangles to kind of figure out what the areas of those rectangles are and then add them all together. So step 2 is to form small approximating rectangles using continuous functions on the subintervals from a to b. Okay, so then we're going to find a way to find the measurements of those rectangles. So each one of these rectangles, to find the area of them, right, we need a height and we need a base. The height of each rectangle would be the upper function minus the lower function at whatever point that is. Right, so this is going to be the upper function, which is f. So we have f of x at some point minus g of x at some point. That's our height. And then our base is just whatever that change of x is. Okay, so to find the area of one of those rectangles, we'll take f of x minus g of x, and then the base is going to be whatever that change of x is. So to find the area, we have the upper function minus the lower function, and that quantity times the change in x. So when we add those areas all up, similarly to how we did with Riemann sums, we take the summation of the upper function minus the lower function times the change of x. And when we take the limit of that, that's what gets us to the integral. Okay, so to find the area between two functions, we take the integral on the interval from a to b of the upper function minus the lower function. So this is upper minus lower times dx, which is our change of x. So if f and g are continuous, which is very important, if they're continuous with f of x being greater than or equal to g of x throughout the interval from a to b, then the area between f of x and g of x from a to b is found by taking the integral from a to b of f of x, which is our upper, minus g of x, which is our lower, dx. So our first example, we want to find the area between the curves y equals secant squared x and y equals sine x from 0 to pi over 4. So our first step is to determine which curve is the upper curve and which curve is the lower curve and sketch the graphs. So using a calculator, just plugging in secant squared x and sine x, you can see that secant squared x is the upper function and sine x is our lower function. So now we want to draw a representative rectangle in the region. So just going to draw a rectangle in here. And you can see that if we draw a rectangle in here, then the height should be secant squared x minus sine x, and our base is our change of x, which we'll rewrite as dx. So if we're going to write an integral to find that area, then the area goes from 0 to pi over 4, and our upper function is secant squared x, and our lower function sine x. And then our change of x is dx. So if we want to integrate this, we can split these since they're separated by subtraction. And we'll have the integral from 0 to pi over 4 of secant squared x dx minus 0 to pi over 4 sine x dx. And if I integrate this, the antiderivative of secant squared x is tangent of x. The antiderivative of sine x is negative cosine x. And we're integrating from 0 to pi over 4. Okay, so now we're going to have tan pi over 4 plus cosine pi over 4 minus tangent of 0 plus cosine of 0. So we get 1 plus 1 over root 2 minus 0 minus 1, which is equal to 1 over root 2, or can we write it as root 2 over 2? Okay, you could also plug this into the calculator. As well, then you'll get the same answer. So now we want to find the area of the region enclosed by the parabola 2 minus x squared and the line y equals negative x. So we're going to sketch approximately what these two graphs look like. So 2 minus x squared, something like that. Y equals negative x. This is a little bit off, more like a lot of it off, but actually, let me just resketch this. So y equals negative x, goes straight down there, and this is 2 minus x squared. So our upper graph, our upper curve is the y equals 2 minus x squared, and our lower curve is the y equals negative x graph. Okay, so we're trying to find the area in here. So since we only want the area enclosed by the two parabolas, by the parabola and the line, we want to figure out what these points are, what those x values are. Okay, so these two graphs are equal to each other. Negative x equals 2 minus x squared. When x is equal to negative 1 and to 2. Okay, so that means that x equals negative 1, x equals 2, so we're integrating from negative 1 to 2, and our upper graph is 2 minus x squared, and our lower graph is negative x. So if you're wondering how I got negative 1 and 2, I'll do the work out here. So we had negative x is equal to 2 minus x squared. Set that equal to 0, so 0 is equal to x squared minus x minus 2. And I can factor that into x minus 2, x plus 1. So then x is equal to 2, and x is equal to negative 1. So that's how we got these 2 points. Okay, and then just going to use that to now figure out what our area would be. So again, we're integrating from -1 to 2 of 2 minus x squared minus -x dx. Alright, so if I simplify that, I'm integrating from -1 to 2 of 2 plus x minus x squared dx. And when I integrate that, I get 2x plus 1/2 x squared minus 1/3 x cubed. We're integrating from -1 to 2. So when I plug in some numbers, get 2 times 2 plus 1/2, 2 squared minus 1/3, 2 cubed, minus 2 times -1 plus 1/2, -1 squared minus 1/3 times -1 cubed. And when I do all of that out, we get 4.5. And that's our final answer. So now for this next problem, we want to find the area of the region in the first quadrant bounded above the curve y equals square root of x and below by the x-axis and the line y equals x minus 2. So we're looking for just this area in here, right? We only want the first quadrant, so we're not looking for this little corner here. Which means that if we draw rectangles here, the rectangles on this side, I'll make them blue, the rectangle over here, that area, that height is going to be square root of x minus this line of 0, with a change of x being the base. But over here, we have a height of square root of x minus 2 and a base of change of x. So we have 2 separate integrals that we're going to have to find here. So our area is going to be equal to, from 0 to 2, right, because this is 2, from 0 to 2, we're looking at square root of x minus 0 dx. And then from 2 to 5, or 2 to 4, excuse me, because this is 4, we're looking at the integral of square root of x minus 2 dx. And that just seems like a lot of work that we shouldn't need to be doing. So instead, another way that we can do this is we can draw horizontal rectangles. Okay, so instead of drawing vertical rectangles that go up and down, we can draw horizontal rectangles that deal with this space. Right, so if I draw a horizontal rectangle instead, then my height is a change in y, and then my base is actually going to be in terms of y. So we need to solve these equations so that they are in terms of y. So to solve this, I'd square both sides. So x is equal to y squared. And then to solve this one, I'd add 2 to both sides so that x is equal to y plus 2. Okay. Then we would use the right function, the right curve, which would be y squared, and we'll subtract the left curve. So we'll subtract y plus 2. Sorry, I do not know my left from my right, clearly. Yeah, so the right function is y plus 2, and the left function is y squared. So right minus left. Just like up minus down, we're doing right minus left. So when we're using horizontal rectangles, we want to take the right curve minus the left curve, and we're in terms of y. Okay. So to find our limits of integration, since we're still looking at this space here, we're starting at 0 in this case, and we're going up to, they intersect at 4, 2, so we're going up to 2 because we're in terms of y. So our limits of integration for this area is going to be from 0 to 2 of y plus 2 minus y squared dy. Okay, and then we would integrate that, plug in our numbers, and we'll get approximately 3.33 is our area. Alright, so for number 4, we want to find the area enclosed by the graphs of y equals x cubed and x equals y squared minus 2. So first thing we want to find is the points of intersection. So these two graphs intersect at -1, -1, and 1.21486, 1.793, so on and so forth. So that's our first step, figure out where they intersect. Our second step is decide whether or not to use vertical rectangles or horizontal rectangles. So if we were to use vertical rectangles here, we'd be fine on the right side, right? We would take our upper minus our lower, upper minus lower, but when we get over here, our upper and our lower are the same function. And because of that, a vertical rectangle would not make sense. So we're going to use our horizontal rectangles. So we're going to draw horizontal rectangles and figure out how we would write this integral. So since we have y equals x cubed, and we're using horizontal rectangles, we want this to be x equals something, right? Because we want this in terms of y, because we're going to have dy. So we're cube rooting both sides, so we'll have the cubed root of y, which is also y to the 1/3. And since we have x equals y squared minus 2, x equals y squared minus 2, which is already in terms of y, so that one's good to go. So our right function is y to the 1/3, and our left function is y squared minus 2, and our interval, since we're in terms of y, it's going to be from -1 to 1.793037. So now we can plug it into our integral. We have y to the 1/3 minus y squared minus 2 dy. We could just plug that into a calculator and we'll get 4.215 approximately. Okay, so for the problem set and for the quiz on Friday, you will not be asked to evaluate and find these areas. You will be asked to set up the different intervals. Okay, so you must know how to set up the interval. Are you using a horizontal rectangle or are you using a vertical rectangle? If you're using a horizontal rectangle, do you have to change information to get it in terms of y, so on and so forth. We'll talk more about this in class, and that's the end of the video.